start the recording. And I want to try some things a little bit different today. But first, I want to share something with you just to get us started off. Let me share the sound too. All right. So this morning, I just want to show you something with. Now, can you all hear the sound? Make sure you turn your sound up. I did try to share the sound with you.
I can hear it.
Okay. Just water. The difference between light that passes through water and reaches our eyes and the light that passes through air and reaches our eyes. So this is just a measuring cup, and I filled it with just regular tap water. And here you can see I drew, whoops, can't quite get it in focus. You can see that I drew 3 arrows pointing to the left on just a plain, actually on the back of an envelope. So if I take these arrows and I put them rather close to the water, actually let me get them real close. You can see how they're magnified. But if I put them back just a little bit further, can you, I'm having a hard time focusing. Can you see the arrows are no longer pointing to the left? They are now pointing to the right. Why is that? That's something I want you to think about. Why did that invert the image? All right, so that's kind of where we're going to start today. That is just a very simple experiment that I did this morning. I was trying to think about how to start off, light and optics, and we're going to review waves as well today. But I want you to think about that. First of all, what do you think? Let's have Kira, just because you're right beside of my head in my video. Kira, what do you think might be going on?
Maybe it's because it's water bends.
That is perfect. Yes, the water changes the direction of the light. You're exactly right. And that is what we're going to talk about today. The water acts just like a lens in my glasses, a lens in a camera, a lens in a telescope or a microscope. The water acts like a lens, and it can magnify. It can also invert images. And so that all deals with what you'll be looking at this week with geometric optics, which sounds a lot harder than it really has to be. So today I want to try something that is different. I'm going to put you on a Nearpod lesson. And so let me see if I can, just give me a second. And I will bring that up for you. We're going to start with the review of waves and kind of get into a little more in depth. So I'm going to share my screen, if I can find my Zoom again. All right. And you will need to be in Zoom, but also make sure that on your computer you access this. Hold on one second. I'm going to share Nearpod. So on your device, And it doesn't matter if you're on your phone. It's a little bit harder to see on a phone, but it truly doesn't matter. Nearpod is device agnostic. So on your computer, even while you're in Zoom, open up a tab, and I want you to go to join.nearpod.com. And then you are going to join a lesson. And that's the code you're going to put in. So if you could do that right now. And tell me when you guys are in.
I got in.
Okay. Girls, how about you?
I'm in. I'm in.
I'm not yet.
Okay, I'll leave it there for a few more seconds. Did you get it?
Almost, not yet.
It's okay. All right. You should still be able to see the join code in your upper left. All right. So my background is in geology. That is like my strength. And so I'm going to relate waves not only to physics, but also to other things here on the earth. So we're going to kind of review from last week, and let's get started with a review right now. So you should see a quiz. Can you all see it? Not in Zoom, but on your Nearpod.
Yes, sorry, I was talking. Didn't realize I
No.
was muted.
You're fine. You're fine. So go ahead and just answer those questions. And I promise it's not actually for a grade. I just want to see how much you know or how much you remember. There we go. I've got some people starting to answer. There we go. And let's see here. So Nearpod is really weird in this respect. Can you, let's see here. Let's have Jenna. Could you read the first question? And make sure you're unmuted.
If you are measuring with a ruler that marks units to the hundredths place, what unit is this?
All right. And what did you answer?
Millimeters?
That's close. That's to the thousandths place. It
Oh,
is.
darn.
That's okay. That's centimeters. And it's just a review. And Jenna, pick somebody for question number 2.
Is Ben here?
Yes, he is. All right, Ben,
Okay.
read question 2 for us.
Alrighty. How many significant figures are in the number 105? I said it was 3.
And you are correct. Because a 0, if it's in between 2 numbers that are not 0, then it becomes significant. So good. And let's see. Ben, pick one of the other students to read number 3.
Well, I think Kinsey has to because Kira's already read today.
Okay.
What unit do we measure frequency in? And I put hertz.
All right, good. All right. That was just some of the things that we had from last week. And we are going to do a little drawing activity. And so I want you to draw a wave for me. And any type of wave, a light wave, a sound wave, a water wave, a seismic wave. And then I want you to label any parts that you know. Okay, I see Ben's waves. I see Jenna starting. Good. Excellent. And Kinsey and Kira, I'm still waiting. Good. Very good. So we've got the crest from Jenna. We've got wavelength, which is correct. And Ben has labeled peak or crest. And you're right, they are both correct terms. Usually we refer to it as the crest. And I see a nice long wave for Kira. Excuse me. All right. And I like this because I can see what you are remembering, and I see wavelength and I see valley. We usually refer to it as a trough. All right. So I want to, here's Jenna's. Very good. And then at the bottom right here is the trough of the wave. And let's see. That's good. And Kira's, I see a nice long wavelength. All right. Good. Thank you. And so you guys all have an idea about the anatomy of a wave, but I want to show you in this everything that we usually think about when we think about waves. The crest is the top of the wave and the trough is the bottom. Wavelength can actually be measured from crest to crest, excuse me, or trough to trough, either one. Amplitude is the height of the wave from the normal. And so this line is the normal part, or you could think about it like the surface of the ocean. And amplitude is from the surface to the top, or it's from the surface to the trough of the wave. Either one can measure amplitude, and amplitude is simply the height. That's all that is. And so what can we measure? So you guys went through the electromagnetic spectrum, and you learned the formula for measuring wavelength, frequency, and velocity. And they all mean different things. A wavelength is just measured from crest to crest or trough to trough. It's the distance between the peaks of two waves. Frequency it's basically how many waves go past us in a given amount of time. And a hertz is just 1/seconds. It's 1 unit of whatever over a second. And that's what a hertz is. So if you were standing in the ocean, just up to your knees, however fast waves went past you would be their frequency. And then velocity, of course, is actually the speed. It's how far the wave travels over a given amount of time. And that's measured in meters per second. And there are a couple basic types of waves. And one type of wave that we'll work with today is the transverse wave. And it travels perpendicular to the force. So if the force is coming from the left side, the wave is actually going to be traveling up and down. And so water acts that way, but so does a light wave. However, one thing I want you to remember, and you can put this in your notes, and like I said, this is being recorded, and so you can go back and watch this and put it in your notebook. But water is a mechanical wave, whereas light is a non-mechanical wave. And that's going to come into play here in a little bit, because transverse waves on Earth act differently than they do in outer space. The second type of wave is a longitudinal or a compression wave. And these are important to you because this is what a sound wave is. It is a compression wave. And so it runs parallel to the direction of the force. So if I push it from the left, the wave is going to travel from left to right. It'll go parallel to that force. And these are pretty neat because they travel through all kinds of mediums. And so what happens to a wave? Basically, a wave travels in a straight line until it runs into something. And then things can happen. It can basically be reflected. And so that wave can either come back to you as an echo if it's a sound wave, or it can reach your eyes as a reflection from a mirror. It can be absorbed. If you've ever been in a soundproof room, those tiles in that room absorb sound waves. The same thing happens with if you're outside in the summertime and you have a dark shirt on, it is absorbing those electromagnetic radiation waves. And so you can feel yourself get hotter. Or it could be refracted, where it is actually, the light is actually bent. And that's because the medium changes. A good example of that is a rainbow. So the light is traveling in a straight line, and then it interacts with the water of a rainstorm, and it bends and it separates out the light. So that's what refraction is. And the kinds of waves that we're going to deal with are light waves. And remember, light waves are transverse waves, but they are non-mechanical. That means they can travel in a vacuum, that they don't have to travel through a solid, a liquid, or a gas, but they can. Light can travel through solids, well, opaque or translucent solids. It can travel through liquids that are clear, as well as through the air or through a gas. But the neat thing about light is that a light wave doesn't have to have a medium. It can travel through space without that. Then we have seismic waves. So these are like our earthquake waves. These are compression waves, but they're also transverse. Some of the waves of earthquakes are both. They're a combination of compression and transverse waves. And the medium that they travel through, it depends on the type of wave. And so a transverse wave in the earth is called a mechanical transverse wave, and it can only travel through rock. In fact, that's one of the ways we discovered that the inside of the earth was liquid, the very inside, or molten, I should say. Because the waves, some of the waves of earthquakes take longer to get to a seismometer where it measures, because they can't travel through parts of the mantle. Parts of the mantle, or the largest part of the center of the earth, is partially molten towards the bottom, and it can't travel through that. But then we have compressional waves, and those waves can travel through everything. And those are the very first waves that will reach the measuring points or the seismometers on the earth. And that's because it can travel through solids and liquids. Finally, we have sound waves. And sound waves are longitudinal or compressional waves. Those are the same things. Longitudinal, compressional waves, that's just two names for the same type of wave. It's like a slinky. If you've ever played with a slinky and it goes back and forth, or if you think about an accordion. So if you've ever been to the Italian Heritage Festival here in Clarksburg, you know that there were two guys, Mel and Ott, that played accordions. And so that accordion goes back and forth. That's the way a sound wave looks like if you were to visually see it. And sound waves can travel through solids, liquids, and gases. So again, I used to have a GIF of these so that you could actually see them. But this P wave is a seismic wave. These are the compression waves, and they go back and forth like the accordion, and they don't really disturb the medium, but they run straight through it. The other type of wave is the transverse wave, and it pushes, the force comes from either the right or the left, and then the wave itself acts parallel to it. I'm sorry, it acts perpendicular to it. Sorry about that. But it goes up and down. So if this is coming from left to right, the wave itself will be up and down perpendicular to that force. And then love waves and Rayleigh waves, you guys don't need to know about that. But they are actually a combination between compression waves and transverse waves. And so different things affect sound waves. And I want you to think, would sound travel faster through the air, through water, or through a block of wood? Kira, I think I picked on you last. Could you pick somebody to answer that question?
I'll pick Ben.
All right, Ben. So would a sound wave travel faster through the air, through water, or through a block of wood?
Hmm. For some reason, I feel like air is so obvious it can't be the right answer. Like, I feel like it'd just be too easy.
I
But I don't know.
understand that.
For some reason, I'm kind of thinking wood. I don't know why. I just
Yes,
was.
good. Yay, you're right. And let's talk about why he's right. So I want you to think about a wave. Remember how I said that it has to encounter something? Well, I
Yeah.
want you to think about how the atoms are arranged in solids, liquids, and gases. And so in a solid, like in a block of wood, the atoms are packed really tight together. And so that sound wave is going to hit off of an atom faster as it travels through that block of wood. And so it'll go, atom, 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 atom. It's going to go through really fast. Liquids, the atoms are still closely packed, but there's no regular arrangement. And so that's why sound, if you've ever been in a swimming pool, like when you were a kid and you tried to yell at somebody underwater, it sounds different because it travels differently. And so it's hitting the atoms, but it's actually slowing down because it takes a little bit longer to reach each of the next atoms. And then gases, we are very used to the way that sounds. And so we imagine that, oh, well, it must travel fast through a gas. But actually, no, because the atoms are very separated in air and there's no regular arrangement. So we kind of just, it travels slower through the air because of that. So good thinking. And then if you want to take a look at, I've just put together some of the velocities of waves. And if you look at how fast sound travels in a solid, it's about 5,000 meters per second. And of course, that depends on which solid we're talking about, but just in general, on an average, it travels 5,000 meters per second. Sound in water is about 1,500 meters per second. And in air, it only travels 335 meters per second. So, you can actually see numerically that, yeah, you're right, Ben. It really does travel faster in a solid. Whereas light, holy cow. Of course, you guys had to work with this last week, but it's 3 times 10 to the 8th meters per second. And that's also why if you've ever watched somebody dribble a basketball from far away, you see the basketball hit and almost reach their hands before you hear the sound of that basketball. Whoops, and I didn't finish that one. So I talked a little bit about seismic waves. I want to show you this. All right, now let me stop one of this. Let me click a different share screen. All right, so what I have here is, I hope it lets me do this. Click anywhere to launch a seismic wave. All right, so, oh shoot, it may not be letting me. There we go. So here is just a model of the Earth. And the reason I want to show you this is because in physics, when I teach about waves and especially light, it acts so much different than the waves that are on the Earth. And so we can see underwater mountains, sea caps. This is, of course, the Pacific Ocean over here. And then we also have, we have the mantle, the outer core and the inner core of the earth. Now, just for reference, because this is not an earth science class, the mantle is molten. So when you think about magma, that's basically what the mantle is. The upper mantle, close to the surface of the earth, is kind of rocky. We call it plastic because it's a rock that acts like a liquid. It's kind of weird. And then as it gets closer to the core, it becomes more and more molten. So the lava that comes out of volcanoes, that's kind of what it looks like down here towards the center. The outer core of the earth. The outer core of the earth is more of a liquid. Now, we still consider it molten, but it's more of a liquid, and I'll show you in just a second why this is important. And then the inner core is actually solid. Outer core is made up of 3 magnetic metals, nickel, cobalt, and iron. Those are the only 3 metals on Earth that are naturally magnetic. And this rotates around the inner core, and it creates a magnetic field around the Earth, which is why we are not bombarded with some of the deadly rays that come from the sun. And I'm talking about, if you remember your electromagnetic spectrum, it protects us from like gamma rays. It protects us from X-rays actually entering the Earth's atmosphere. So I am going to press play so that you can see the waves. And remember, the compression waves are going to be the fastest because they can travel through solid and liquid. And then the transverse waves, the mechanical transverse waves, will not. So let me show you that. So I just started an earthquake. These P waves are the compression waves. And I want you to see they do refract because they are encountering a different medium. But look at the S waves. The S waves are the transverse waves. They will not travel through liquid. Sorry, my dog is hearing these noises and thinks it's playtime. All right. So when we talk about waves and we talk about how they act when they pass through different mediums, it's not just light waves that do that. It is all types of waves. So seismic waves, and you don't have to understand anything except looking at the color red. Do you see how the red waves, where my pointer is, the red wave is bouncing and changing direction? That's because at the top of the mantle, it's solid and liquid together. And so but there's a lot of rock. And so those mechanical transverse waves, it can still travel through there, but it cannot reach the outer core. This is how we found out that the outer core of the Earth was liquid, because these mechanical transverse waves, they can't pass through it. So let me stop that and then share with you the Nearpod again. Whoops. All right, can you see the Nearpod again?
Yeah.
Okay, I just like to make sure. So like I said, the earthquake waves, we're not going to go over body waves and surface waves because that doesn't apply to you. this is just showing you the effects of waves. So when you have, I want you to take a look at these train tracks. So when a wave hits from an earthquake, a seismic wave, they can actually cause the features on the surface of the earth to mimic the waves that are passing through. So I just thought that was really interesting. All right. And finally, a water wave. So I think we've all heard of, let me go back here, tsunamis. We used to call them tidal waves, but they're not related to the tides at all. It's a different type of wave. This is a water wave, and they are caused by the plates of the earth. Basically, it gets stuck, and over time, it begins to bend the rock above it. And then finally, it snaps. And so as it snaps, the bottom of the ocean basically drops, and it creates a wave above it. And then it creates one perpendicular, and then it spreads out. And that's how a tsunami works. So let me stop this one. And that was basically a review of waves and the things that you had from last week. Do you all have questions about the electromagnetic spectrum? Or Martina showed me your your progress in the class, and so most of you have gotten through all that. But are there any lingering questions that you have? All right, then I'm going to stop that Nearpod. All right, and I'm going to give you a different one. So is everybody out of their Nearpod lesson?
I'm in one with like Alaska now.
Oh, sorry about that. I forgot to stop it. Let me go back to it. All right, I'm going to flip through here until it stops. All right. We're going to end that session. All right, now is everybody out of there?
Now I am.
Okay. All right, and so I will assume that the girls are too. I am going to share something else with you. And we are going to start right into light. All right, I want you to go to join.nearpod.com. And I want you to enter this code. All right, I see one of you has joined. All right. So we are going to take a look at light and hopefully and optics. So let's go ahead and get started. And I am going to, oh, that's not the one I wanted to show you. All right. So let's see. So what is light? Jenna? If you had to answer the question, what is light? How would you answer that?
Oh my, I don't even know.
That's okay. What do you know about light?
Mm, the reflection of light's how we see colors.
Okay. Very good. Kira, what do you know about light?
It makes us be able to see everything.
Okay. And I'm missing a sister, and I can't think of your name right now, honey. Kinsey, tell me what you know about light.
They said what I know about light. I don't know anything else.
Okay. Ben, anything else?
I mean, not really. No, sorry.
Okay. No, that's okay. I just need to know where we start. So hopefully by the end of this, you will be able to describe light and explain why we only see such a tiny portion of it. And so basically today, I want this to serve as like an introduction to it, both to light and to vision. So let's get started. And I just want you can either draw what light is, you can show me what light is. If you had to show, let's say, a second grader what light is, how would you draw that? Good. Good. We have one of our very basic sources of light, which is the sun. Thank heavens for the sun because it is the source of all the energy on earth. I should say the beginning of the energy on earth. And good. And I see light passing through, creating a rainbow. Ben, I am assuming that is a light bulb.
A second grade drawing of one, yeah.
Okay, no problem. Okay, so we have artificial light sources, we have natural light sources. Good. So this is a perfect place to start. So this is a collaboration board. And I just want you to write down as many sources of light as you can name. Let me see if I can add a timer. Nope, I can't. But I want you to do that. I'm going to time you. So as many sources of light as you can think of in 30 seconds. Ready? Go. 15 more seconds. Awesome. All right. So let's stop here. I see the sun, a light bulb, a lamp. I see a candle, good, which is fire. Jenna gave me a whole ton of them. A light bulb, the moon. So how does the moon provide us light?
Isn't it from the sun?
Yes, it is a reflective surface.
That's why, like, sometimes when we have lunar eclipses, it's because the moon or the sun's in front of the moon, right? Is that how it works? Or do I have it backwards?
For a lunar eclipse, the earth passes in between
The sun.
yeah, the sun and the moon. And so
I knew it
you could
involved three of them.
exactly. Fireflies. Oh, that is excellent. I wasn't even thinking about bioluminescence, but nature can naturally provide glowing light. And of course, lightning, which is, you know, how we have solids, liquids, gases. Lightning is actually a plasma. And it is basically, it gets so hot that the atoms split apart. So excellent sources of light. And they all act differently. We have light from nature. We have light from man-made objects. We have fire. Good. So we have an idea of where light comes from. So let's think about that and explore that a little bit more. So on this next slide, we're going to take a look at a 3D model of a microwave oven. I want you to think about a microwave, how it works, and whether or not you think a microwave is a source of light. So it's just 17 seconds. Okay, so I have no idea exactly how that microwave works, but I have an idea about microwaves themselves. So I know it says think, pair, share, and this is what I use when I have gigantic classes. So are the microwaves inside of a microwave oven? Do they represent a kind of light? I just want you to think about it. You don't have to say it out loud. I just want you to think. But remember, like, never be afraid of being wrong. Please. There are, what, 5 of us or 6 of us here in this room. We're fine. So, do you think radio waves and X-rays are a type of light? All right, Kira, Jenna, just, it doesn't matter. You can just, whatever you think. Okay, we've got about a 50-50 split in this room. So we've got some of you that think, yeah, I think radio waves and X-rays are a type of light. Kenzie, why did you pick yes?
Well, I know that X-rays, like, there's a light when you get an X-ray,
Very good.
but I don't know if that has any part to do with it or if it's just a light.
it has a lot to do with it. So, and we're going to discuss that further. Kira, why did you say no? The radio waves and X-rays are not a type of light.
I didn't think radio waves gave off any light, so I put no.
Okay, that is fair. That's a legitimate. So let's take a look and learn a little bit more. So what is light? We're going to watch a video that explains the concept of light. And then I want you to rethink what you know about light. Before I start this, you should have read about the electromagnetic spectrum last week. And it starts all the way down at the bottom. There, again, Pierpont is trying to give me access. I was supposed to have access yesterday. I still do not, but they are working on it. I don't know what's going on exactly, but anyway, once I get on there, I have a picture that I like to show my students about the electromagnetic spectrum. And it starts at the low end, or the great big waves that we can actually measure in kilometers, the radio waves. They're big, lazy, low energy waves, all the way up through microwaves, infrared rays, visible light, ultraviolet light, X-rays, and gamma rays. So when a star like our sun, and this is of course any star in the universe, but when the sun emits light, every single ray of light contains all of that, from radio waves all the way up to gamma rays. And so those are all light. However, because our bodies are only set up to perceive a very tiny portion of the electromagnetic spectrum, we don't see that. And so let me share this video with you. Listen, it's kind of cheesy, but it gets the point across.
What if you could only see one color? Imagine, for instance, that you could only see things that were red, and that everything else was completely invisible.
All right, now can you guys hear the sound as well?
Yeah.
Okay.
To you. As it turns out, that's how you live your life all the time, because your eyes can only see a minuscule part of the full spectrum of light. Different kinds of light are all around you every day, but are invisible to the human eye. From the radio waves that carry your favorite songs, to the X-rays doctors use to see inside of you, to the microwaves that heat up your food. In order to understand how these can all be light, we'll need to know a thing or two about what light is. Light is electromagnetic radiation that acts like both a wave and a particle. Light waves are kind of like waves on the ocean. There are big waves and small waves, waves that crash on the shore one right after the other, and waves that only roll in every so often. The size of a wave is called its wavelength, and how often it comes by is called its frequency. Imagine being a boat in that ocean, bobbing up and down as the waves go by. If the waves that day have long wavelengths, they'll make you bob only so often, or at a low frequency. If the waves instead have short wavelengths, they'll be close together and you'll bob up and down much more often, at a high frequency. Different kinds of light are all waves, they just have different wavelengths and frequencies. If you know the wavelength or frequency of a wave of light, you can also figure out its energy. Long wavelengths have low energies, while short wavelengths have high energies. It's easy to remember if you think about being in that boat. If you were out sailing on a day with short, choppy waves, you'd probably be pretty high energy yourself, running around to keep things from falling over. But on a long wavelength sea, you'd be rolling along, relaxed, low energy. The energy of light tells us how it will interact with matter, for example, the cells of our eyes. When we see, It's because the energy of light stimulates a receptor in our eye called the retina. Our retina are only sensitive to light with a very small range in energy, and so we call that range of light visible light. Inside our retina are special receptors called rods and cones. The rods measure brightness, so we know how much light there is. The cones are in charge of what color of light we see, because different cones are sensitive to different energies of light. Some cones are more excited by light that is long wavelength and low energy, and other cones are more excited by short wavelength, high energy light. When light hits our eye, the relative amount of energy each cone measures signals our brain to perceive colors. The rainbow we perceive is actually visible light in order of its energy. At one side of the rainbow is low energy light, we see as red, and at the other side is high energy light, we see as blue. If light shines on us that has an energy our retina can't measure, we won't be able to see it. Light that is too short wavelength or high energy gets absorbed by the eye's surface before it can even get to the retina, and light that is too long wavelength doesn't have enough energy to stimulate our retina at all. The only thing that makes one kind of light different from another is its wavelength. Radio waves have long wavelengths, while X-rays have short wavelengths, and visible light, the kind you can actually see, is somewhere in between. Even though our eyes can't detect light outside of the visible range, we can build special detectors that are stimulated by these other wavelengths of light, kind of like digital eyes. With these devices, we can measure the light that is there, even though we can't see it ourselves. So take a step back and think about all of this for a moment. Even though they seem different, the warmth you feel from a crackling fire is the same as the sun shining on you on a beautiful day. The same as ultraviolet light you put on sunscreen to protect yourself from. The same thing as your TV, your radio, and your microwave. Now, those examples are all things here on Earth, things you experience in your everyday life. But here's something even more amazing. Our universe gives off the full spectrum of light, too. When you think of the night sky, you probably think of being able to see the stars shining with your own eyes. But that's just visible light, which you now know is only a tiny part of the full spectrum. If we had to draw the universe and could only use visible light, it'd be like having only one crayon. Pretty sad. To see the universe in its full spectrum, we need to have the right eyes. And that means using special telescopes that can help us see beyond visible light. You've probably heard of the Hubble Space Telescope and seen its beautiful pictures taken in visible and ultraviolet light. But you might not know that there are almost 20 space telescopes in orbit, missions that can each see part of the full spectrum of light. With telescopes acting as our virtual eyes, both in space and here on Earth, we can see some amazing things. And the coolest thing of all? No matter the wavelength or energy, the light that we see out in the distant universe is the same thing as the light that we can experience and study here on Earth. So since we know the physics of how X-ray, ultraviolet light, or microwaves work here, we can study the light of a distant star or galaxy and know what kinds of things are happening there too. So as you go about your daily life, think beyond what your eyes can and can't see. Knowing just a little bit about the natural world can help you perceive the full spectrum around you all the time.
All right. So on the next slide, I know it says partner quiz, but it's basically all of us. And so, but you can discuss each question and justify your answer as long as you use evidence to back it up. I'll tell you what, let's just do this together. Ben, could you read question 1?
Sorry. Radio waves, X-rays, and microwaves are all forms of light. Do you want me to answer too?
Yeah, go ahead.
I said it's true.
Exactly. That is true. Kira, you're next.
What is the definition of light? Choose the best answer. I think C.
What is You have to realize I can't see the questions.
Okay. Electromagnetic radiation that acts like both a wave and a particle.
Perfect. Yes, that is correct. Kenzie, how about the next one?
Which term refers to the number of waves that pass in a fixed place in a given amount of time? B, frequency.
Good. Very good. Jenna?
If a wave of light has a long wavelength, it has a low energy.
Exactly. Very low energy. All right, back to you, Ben.
Inside our retinas, cones are in charge of measuring brightness, right?
I believe so, yes.
Because the rods dictate how much light we see, right?
Yes.
Got it. Look at me.
Kira? Oh, we got that backwards.
I did.
Yeah, so it should have been the cones. That's okay. That's okay. That's something you can always read over. Kira, what's the last one?
The rainbow we perceive is visible light in order of its energy. I think that's true.
That is true. Red is the lowest energy. Red, orange, yellow, green, blue, indigo, violet. Those are all orders of energy. The red has the longest wavelength, therefore the lowest energy, while the violet and ultraviolet have very very short wavelengths, which means they have high energy. Good job, guys. Very nice. All right. I'm going to skip over this one today. And so how do our eyes see colors? And that was something that one of you has already answered. The colors that we see are the wavelengths reflected back to our eyes, while all other wavelengths become absorbed by that object, whatever it is. But why can't we see ultraviolet or infrared light? Well, the ultraviolet, that wavelength is so high energy that it doesn't even pass through our retinas. But the infrared light has lower energy and it has a longer wavelength, and the rods and the cones are not stimulated by it because there's just not quite enough energy to actually get our rods and cones started. Now, I'm going to play a video for you, and I don't want you to feel overwhelmed, but if you've ever seen a crash course video before, it can be overwhelming. I am going to make sure that you guys have access to the video all by itself after class today, so that you can start it and stop it as needed. So this is a very good explanation of optics. I just want you to kind of relax. You don't have to take notes right this instant because this goes fast. Okay, but when you have access to the video, you can start it and stop it and take notes as you need to. But we're going to watch this together. Oh, this is not the one.
Sunlight, moonlight, torchlight and flashlight, they all come from different places, but they're all the very same thing. Light. It's what makes it possible for us to see the world around us, so it's worth a close, hard look. For instance, how does light travel? When you flip that switch in the bathroom to brush your teeth, how does light move from the light bulb to the mirror and into your eyes? And if you're one of the many people who wear glasses, how do those lenses turn a blurry world into a high-definition experience? Whether it's glasses, microscopes, or telescopes, it's all about bending light to our will. How do we go about this grand task of controlling the very thing that helps us see? Well, let's take a look. No matter where light comes from, we generally talk about it in the same way and make the same assumptions about how it travels. Say you're lying on the beach, basking in a ray of sunshine. One of the first assumptions we make is that the light is traveling from the sun to you in a straight line. This way of thinking about light is called the ray model, and the core tenet of the model is that light travels in straight line paths called rays. But each individual ray is really just a graphical representation of actual light. A light source may be emitting an infinite number of rays, but we only draw a few to get the point across. Now let's say we have a flashlight that's emitting rays of light. If we point the flashlight at a reflective surface like a calm pool of water, we can trace the rays as lines that leave the flashlight, reflect off the water, and continue on as a straight line. Note that the rays on top of the flashlight are now on the bottom, and vice versa. This makes sense because if you're viewing something in a reflection, you see its image reverse. Another important observation is that rays leave the reflected surface at the same angle at which they struck it. So if I point the flashlight at a 30-degree angle, an angle that we call the angle of incidence, it would leave at a 30-degree angle in the other direction. So we'd say that the angle of reflection is equal to the angle of incidence. And
All right. In your notebook, this is something that's very important, that the angle of incidence, so wherever a ray of light comes from, it leaves or is reflected at the exact same angle. So like she said, if it is 30 degrees into the water, it will be reflected at 30 degrees out of the water. If it's 75 degrees in, it'll be 75 degrees out. And so that's a very important concept.
And the fact that these two angles equal each other is called the law of reflection. Now, the way I described the light hitting the pool of water was oversimplified, wasn't it? Because in reality, some of the incident light will reflect off the water's surface, while the rest of it will go into the water. And an interesting phenomenon happens when light waves change from one medium to another, such as going from air into water. Have you ever looked at a straw sitting in a cup of water and noticed how the submerged part of the straw looks bent? Of course, the straw itself isn't bent, but the light is when it passes between the water and the air. This phenomenon of light rays changing direction at the interface between media is called refraction. When a ray moves from air into water, the ray's angle after passing into the water will be less than the incident angle. So the straw looks bent because the rays coming from the straw into your eyes don't travel on a straight path. They become bent so the bottom of the straw appears to be in a place where it's not. The angle of a light ray after it passes from one medium to another is called the angle of refraction, and it's related to the angle of incidence by Snell's law. Snell's law says that the angles of refraction are determined by the index of refraction for each medium and the angle of incidence.
All right. So some of this goes a little more in depth than what you'll need. However, it's here in case any of our activities that you'll be doing this week refer to it.
The index of refraction for a certain medium is the ratio of the speed of light in a vacuum versus the speed in that medium. And when a ray enters a medium with an increased index of refraction, the angle of refraction decreases. In other words, the higher the index of refraction, the smaller the angle. And refraction occurs when light leaves a medium too. Say you have a flat piece of glass standing on end and a light ray enters the glass at an incident angle of θ1. The angle of refraction inside the glass would be less than θ1, since the index of refraction of glass is greater. But once the ray reaches the interface between the glass and the air on the other side, it refracts again, and now the angle of refraction is equal to that first incident angle. So if
All right, another thing I'd like to point out is this symbol is what we use, we refer to it as theta, and theta is just a variable that we refer to as unknown angles. You know how like in an algebra problem, you'll be like 1 plus x equals 4, and x stands for that number. When we talk about angles, we use, instead of x, we use theta. And so when you see that symbol, that's all it means. It just means, hey, this is an angle that we don't really know. And this is the first angle, and then this is the second angle. So this angle is in the air, which means this is the same. It's also in the air. They give this one a number 2 simply because it's a different medium. It's glass.
So if you look at the right side of the glass, your eyes see an object that appears to be lower than it actually is. Now, when you observe an object through refracted light like this, what you're seeing is an image, a visually reproduced copy of an object, and not all images are the same. An image is considered to be a real image if the rays from an object converge at some location, such as your eye or some other surface like film. Real images can be projected onto screens because light rays from an object are actually travelling there. But the alternative is a virtual image, an image where the light rays don't actually converge, so your eyes construct an image as if the diverging rays originated from a single point. When you look in the mirror, for example, it looks like you're standing on the other side of the mirror, but you aren't. You're seeing a virtual image because the light rays that make up your reflection aren't actually converging to form an image of you. Now, what if we take that plate of glass and reform both sides so they're no longer flat? How does that change the law of refraction? It doesn't. Refraction still occurs, it's just that the normal line, which is the imaginary line that the angles are relative to, changes. Warped pieces of material that form images of objects are lenses, and they're the most critical tool in the field of optics. Say we have a lens that has a spherical face on both sides, known as a convex lens. As light rays enter the lens, they turn slightly towards the axis of the lens, the imaginary line that runs through its centre, perpendicular to its face. As they leave the lens and move back through the air, the rays are angled slightly more toward the central axis due to the lens's curvature. The rays on the very top and bottom of the lens are bent at a larger angle towards the central axis than the rays near the centre, which stay almost parallel, and they all eventually converge at a single point called the focal point.
All right. So bear with me. So all of the rays are converging at this point once they pass through this convex lens. I want you to think now, since all of the rays are at one point, is the image that we see, is it going to be real or is it going to be virtual? So just think about that.
Think of a magnifying glass. If you hold it just right in the sunlight, you can concentrate the sun's rays into a single, very hot point. That works because you've taken a bunch of incoming parallel rays and placed your target of choice at the focal length of the magnifying glass. That's the distance between the lens and its focal point. And one measure of a lens is its power, which is expressed simply as 1 over the focal length. But a lens that causes light rays to converge in this way is known as a converging lens. And when you look through a converging lens, you can see real images from objects that are beyond the focal point. This is
all right. So these are real images. When all of the, notice that I'm skipping over some of the stuff that's more in depth. When the rays are all converging at a single point, it forms a real image. So, and then we'll take a look at what a virtual image is.
This is because light rays from those objects actually converge after passing through the lens. And remember, when rays converge at a point, that means a real image has been formed. Let's show this using a ray diagram, which tells us about the position and size of images as seen through a lens. Let's take a candle that's some distance from the lens, which we'll call the object distance. We'll use the object distance and the focal length of the lens to find the image distance, the location where the image forms on the other side of the lens. Lenses have the same focal length on both sides, so we'll label the focal point on the side opposite of the object as f, and the point on the same side as the object as f prime. Now, we know that the ray travelling parallel to the axis will pass through the focal point on the other side, so let's draw a ray from the top of the candle, refracting through the lens, and then passing straight through the focal point f. Since the focal length is the same on both sides, we draw a second ray from the top of the candle through the f prime focal point, which then refracts through the lens and travels parallel to the axis. The third ray travels straight through the centre of the lens. We draw this line because if we assume a thin lens, then we can draw a straight line through the centre and disregard the slight offset that would occur due to refraction. With these 3 rays in place, we see that they intersect at a single point, representing the top of the candle in the newly formed image. You might notice that the image is upside down, which will always be the case for convex lenses, and the image is formed by light rays that actually originated from the object, so a real image is formed.
All right, that'll be another thing that I'd like you to put in your notebook. Convex the ones that curve out, convex lenses, always form an inverted, it's an upside down image. But it's also a real image, meaning that all of the rays converge into a single focal point. So a converging lens forms a real image. However, that image is going to be upside down, inverted.
Form. The distance between the image and the lens is the image distance, and it's related to the object distance and the focal length by a very important equation. This is the thin lens equation, which is derived from ray diagram geometry. For a single converging lens, the focal length and the object distance will always be positive. The image distance will be positive if the image is on the opposite side of the light source. This equation holds true for converging lenses as well as their opposite, diverging lenses. Diverging lenses have a concave shape and do the opposite of a converging lens, causing rays of light to diverge away from the lens's axis. When we're looking at an object through a diverging lens, our eyes imagine that the diverging rays originate from a location where the rays don't actually begin, so the lens generates a virtual image.
That'll be something else I need in your notebook. Concave lenses that bend inward actually diverge the rays of light. And so those images are called virtual images because they're not really formed from the light. They're constructed by our eyes. But let's take a look a little bit more.
And when we construct a ray diagram for a diverging lens, there are a few key differences. First of all, the focal point F is on the same side as the object, and F prime is on the opposite side. While a single ray of light still goes through the very center of the lens, the other two rays take slightly different paths, resulting in a virtual image forming on the same side as the object itself. For a diverging lens, the thin lens equation is still true, but the focal length is now a negative value. Another important equation that's true for both converging and diverging lenses is the magnification equation. Magnification is the ratio of the image height to the height of the actual object. When the image is upside down, like in our converging lens, then the height is a negative value, and the ratio of the image distance to the object distance is also negative. But all of these ideas taken whole give you a good understanding of optics, the fundamental rules that explain how we can observe particles too small to see with our eyes, as well as objects that are millions of light years away. Today we learned about the ray model of light and the laws of reflection and refraction. We learned about how refraction works with converging and diverging lenses. Finally, we built ray diagrams to discover how objects are viewed through different kinds of lenses at different points. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel and check out a playlist of the latest episodes from shows like It's Okay to Be Smart, The Art Assignment, and Indie Alaska. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course studio. With the help of these amazing people, and our equally amazing graphics team is Thought Cafe.
All right. So when you have access to that video, you're going to stop and start and stop and start and take some good notes in your notebook for that. But Crash Course is exactly the way it sounds. They are quick, fast, dirty introductions to what you guys will be reading this week. And I want you to think about what other questions you still have about light. You do not have to write these right now, but I just want you to make sure that you think, okay, what are we learning this week? So let's take a look at this. I wanted to show you something kind of neat. Animals and ultraviolet light. Animals have different, and by animals, I don't just mean, cute and furry. Insects, birds, anything you can think of that's not a plant. But many animals can see types of light that we can't. And so I want to show you something real quick. Let me see here. Not that. All right. So do you see this? Let me see if I can. Whoops. Sorry about that. So power lines, to us, they just look like normal, lines. But to a lot of animals, they're terrifying. And that's because we can't see what they see. But to any kind of animal that can see ultraviolet light, power lines look like just a series of bursting, popping lights, and they can see all of the energy coming off of the power lines. And according to recent studies, it suggests that high voltage lines really disrupt wildlife behavior more than what scientists previously thought. And that's because power lines give off these ultraviolet blazes of light called corona discharge. And that happens where the power lines aren't very shielded. And so you have these concentration of electrons that rush through the lines. You know, that's what electricity is. However, when the lines aren't shielded, they interact with the air particles and they create ions. They ionize the air. And so it would look like this cascade of glowing plasma, basically like tiny little bolts of lightning coming off of the power line. And they realize that a lot of animals, that's what they see. And now they're using helicopter inspections of these high voltage power lines using using these special UV sensors, and they detect that. One of the reasons they've done that is because birds see that differently than we do. And so here if you're reading, feather patches that to us seem an unremarkable shade of blue are really very, very bright in the UV world. And birds can hunt their prey following urine trails, because if you've ever watched a crime show, you know that UV light reflects, the urine reflects in UV light. And so a lot of these animals have a fourth type of cone that is associated with another dimension of color. And so I just thought that was a really interesting thing that I really wanted to share with you guys, because we don't always see the world the same way as our animal counterparts. All right. And so why can some animals see UV lights? They've got a fourth type of cone in their eyes. All right. So how has your understanding of what light is changed in how you perceive the world around you? So at the beginning of class, we talked about what light is, but by now I think you have a better understanding of the fact that, you know, light just isn't what we see, but that we have all different types of light all around us that we have no perception of, simply because our eyes are not equipped to see any other type of frequency, to see any other type of energy levels. So let's evaluate what you've learned today. Now, it's basically the same question. I want you to describe light in words and in pictures. How is that different from what you understand it to be at the beginning? So just go ahead and draw it or type it. Good. Good, Jenna. Good, Ben. All right, so Kira, I see that sun. Can you tell me a little bit more about what comes in every single ray of light? Kira, can you hear me? You may have accidentally muted yourself.
Yeah, I can hear you.
Okay, so can you tell me like what comes, like every ray of light from a star, from the sun, what does it contain?
I don't know.
Okay. It contains radio waves. It contains microwaves, um, infrared light. It contains visible light, which is obviously something that we see. Ultraviolet. It contains X-rays and it contains gamma rays. So every ray of sun contains that, even though we can't see all of that. And thankfully, things like gamma rays and X-rays don't even reach the surface of the earth. So we're very lucky for that. And so these are things that you will be learning more about this week. But that's good, guys. And that different light, different kinds of light are all around us every day, but we are invisible to it, or it is invisible to us. And you don't have to explain this right now, but the type of light that is visible to humans is simply the visible light spectrum. And so, and again, that is because of the rods and cones, the receptors inside of our physical eyes, that they only perceive the light waves and the energy levels in that visible light spectrum. And I know that throughout the week, you're probably going to still have questions. Please feel free to text me at any time. I know that my name now appears in the course, but as I've told the dean, I personally still cannot access email or the course. And I'm going to, let's see here, end this session for you guys. And going to stop sharing. Do you guys have any questions for me today? Or is that something you'd rather wait on? Go ahead, Ben.
I mean, I'm still kind of confused on how to set my notebook up and what I need to send pictures of in. Like, because it was talking about taking pictures and sending it in of our notebook, but I don't know if you wanted it page by page or if they wanted it of just certain parts.
I'm trying to remember what Martina has told me. You will eventually be sending the whole note, page by page of your notebook. And as far as setting it up, Martina and I were Zooming last night, and you know how anytime anytime we have class like this, there should be a page in your notebook that says class notes, and you can go back and rewatch the class and take some notes. Anytime you do an activity at home, You have to take notes on that. Anytime there's a,
Shut up.
she calls it what, workout problems and explaining. I forget how she says that, but there are places where you have to discussion include in your notebook. I am really hoping that Pierpont includes me today, and then that'll be easier for me to answer your question when I can visibly see what in the world they're assigning to you.
Yeah. I just want to make sure I'm getting what I need to in there and not like messing something up, if that makes sense.
Yeah, I'll tell you what, we have looked at everybody's progress. Those of you who are in class right now, I didn't see any of you, none of you worried me about the progress you're making. And so it looks like you're all right on top of things. Like I told one of you, and I forget who I was texting with, I'm not going to give you late grades until I can get in there. Okay. And
Mhm.
so just because you shouldn't be penalized and I shouldn't be penalized for not being able to access the course yet.
Yeah, that makes sense. I just want I don't know. I got a few things in there right now. Like I said, I just want to make sure I have what I need to and what I don't, or like
Oh,
if I figure out what I don't have.
okay. And if you go through, I think it's my grades on Blackboard, you can see the assignments and
Yeah.
then check and make sure, oh, I didn't see this, and then go back and take a look and see if there's a Dropbox or something that you haven't seen. And I'm also going to try, when I get access, try to like post like a checklist for you guys. A checklist that says, hey, did you make sure you did this, this, and this? That way it's easier to find your assignments and your readings.
Okay.
All right. Does that help, guys?
I have another question.
Sure, Jenna.
One of the work discussion things we were supposed to do, the link wasn't working. So now it said we have to do a YouTube video and that we are going to be given more instructions. I didn't know when we were going to get more instructions though.
Okay, I will talk to Martina today because she did mention that one of the links was broken.
Yeah.
And so I will ask her if she will then post the instructions for that YouTube video by the end of today.
Okay.
All right, yeah, just look for that. All right, well, I'm going to go ahead and end class for you all today. And again, until I send out an email to you, please reach out to me via text. Okay? You
All
guys have a
right.
good day.
Thank you. You too.